Hi everyone, welcome to the fourth video on the Introduction to Deep Learning Theory series. In this video I'm going to focus on the maximum likelihood, the cross-entropy, and one-hot encoding, which is a labeling method when it comes to dealing with multi-class cross-entropy problems. Much of the content of this video is based on Udacity's Intro to Deep Learning with PyTorch by Facebook Artificial Intelligence free course, the link of which you can find up here. But before I begin, let's start with a small recap, which will be crucial when it comes to watching the rest of this video. So far from our previous videos, we have focused on a scenario about acceptance at the university. We defined a neural network that had two inputs, input x1, which refers to the test performance, and input x2, which refers to the grades performance of the students that are candidates for the acceptance at the university. Now, we were given labeled data, which means that we were given historical data that we see here plotted of students based on their scores and grades that got either accepted or rejected. In a binary classification problem such as this one, the label can be either 1 or 0, where 1 refers to acceptance and 0 refers to rejection at the university. Now, to make this easier to see, we visualized our data with blue referring to the labels of 1, which is the acceptance labels, and we painted red the points that refer to label 0 or rejection label. Now, as we saw, we defined a function which produces this line. As we've said, a neural network is a function approximator. So we created this function that best approximates how our data is separated in two halves. Those halves are two probability spaces. Probability space of the people that got accepted, who have label 1, and the probability space of the people that got rejected, that is, people who have label 0. Now, this line is defined by this function, 2x1 plus x2 minus 18. Or in other words, 2 times the test plus grades minus 18. So this defines this specific line. Then we saw an example of some unlabeled data. We had a student that scored 7 at the test and 6 at the grades. And we wanted to classify this person. We want to make some inference and predict if this person would get accepted or rejected. Now, as we see, based on our model, since the point is plotted here, which is the location 7 for the test and 6 for the grades, we see that it's on the probability space of the people that got accepted as it's given by this line. But let's look at this a little bit mathematically, right? Now, we said that this line is 2 times test plus grades minus 18. Now, since the test is 7 here, this is 2 times 7, which is 14, plus 6 for the grades, that gives us 20. Now, 20 minus 18 gives us a result of positive 2. Now, any number that is positive from this function will be on this side of the fence. Any number that is negative will be somewhere on this side of the fence. And any number that is 0 will be somewhere on the line. So now by seeing a +2, we know that this person is on the positive side. And the more positive number, the deeper on the side of the people that got accepted, and the more the negative number, the deeper on the side of the people that got rejected. So since we know already that the higher or the lower the number, the higher or the lower the probability, then we said that we need to somehow measure this. And this is where the sigmoid activation function comes to play. Well, what the sigmoid activation function does, it takes scores and turns them into probabilities. And why is that? Well, you see that the sigmoid activation function that is given here can take any number, negative to positive, and will produce a result between 0 and 1. Thus, we can consider this something between 0 and 100%, right? Now, as we can see, for a given input of a 0, it will produce 0.5 result. And the more the positive our number, the closer to 1, that is 100%. And the less the lower the number, the more into the negative area, the less than 0.5. So what happens here? If I had a point that was here on the line, it would produce a number 0 based on our model. Okay, so this is the line produced by this function, right? And this is our model. For a given test and grades input that produces any number that is somewhere on this line, aka it produces number 0, we would get a sigmoid of 0.5. So that would tell us that we have 50-50 chance of someone to be accepted or rejected, because I mean, you're really on the boundary. You really don't know if you are going to get accepted or rejected, right? Now, the more the positive number, the closer to 1, that is 100% confidence of being accepted. Now, since in our example here, the student who was plotted here scored +2, we see that the +2 gives us plots here when it comes to the sigmoid. And this point is the point 0.88, or 88% confidence of someone to be accepted. Now, by saying a confidence of 88%, we automatically imply that there is also a chance for this person to, by 12%, to be rejected. So now, since we are dealing with a binary classification problem that can be either yes or no, we need for both cases, for both the yes and both the no, to have some possible percentage. So by saying 0.88 at the sigmoid for the point 2, this automatically implies 1 minus the 0.88, which is 0.12 for not being the correct answer, right? So that's what it is when it comes to the sigmoid applied on a score to turn it into probability. Now, let's look at the probabilities here. So I have defined a line here that separates 4 points, okay? So we have created 2 probability spaces. The red probability space for any number that is producing a negative outcome based on our model, and the blue probability space that refers to any number that always based on this line produces positive numbers. So let's take one such number, for example. So we have this point here, which is blue. Now, our prediction is how much likely for a student, let's say, to be accepted, right? So since this is on the positive side, we said that the the sigmoid activation function will take any positive number and turn it to a probability between 0.5 and 1. So since this is 0.6, it means that yes, indeed, it took a positive number and turned it to 0.6. Now, as we also said, this implies that there is the possibility for this point not to be blue. And that is the 1 minus our accepted probability. So by saying reject, we never really predict for rejections. We always predict for acceptance. And our rejection is always 1 minus our acceptance probability. So let's look at a point in this location. Well, here you see that I have the probability of being blue to be 0.3. And that is because always based on our model, this point lays on the negative side of our probability space, okay? So since we have a negative number produced based on the linear function defined by this line, then we know that the sigmoid activation function will take any negative number and turn it into a probability between 0 to 0.5. So by saying 0.3, we already know that we got a negative number here, right? Now, since our probability of acceptance is 0.3 here, this automatically implies that the probability not to be accepted is 1 minus 0.3, which is 0.7. Now, we can say that our model line our model line that depending on the side where each point is, we decide over accepted or 1 minus accepted for our rejection. So now, as you see, because this was our line, we keep this and this as the scores. So we keep the 0.6 and the 1 minus 0.3, which is 0.7 as our scores, right? Now, let's put colors everywhere. So we know so far that our prediction, which is the y hat, is the appliance of the sigmoid activation function on the result coming from our summation of the bias with the weights and our inputs, right? So this is the probability of a point being blue. That's what we are always looking at. Now, let's reveal the colors of the points and see how they really do. Well, as you see, this is a very bad model as it classifies 2 points incorrectly out of the total 4, right? So now let's clean this up and keep the real probabilities based on this model, which are these, okay? Now, let's see what happens in this case. Now, in order to calculate how good or bad this line is doing, let's take into account those probabilities produced. So the 0.1, the 0.6, the 0.7, and 0.2. And let's multiply all these together into that. Now, the product of these probabilities will be the overall probability. And as we see, because we have a bad model, the overall probability is very, very small. It's 0.0084. Now, let's compare this bad model with a better one. Well, here you see that we have a line that definitely separates our data better, right? So we have better probabilities overall. Now, by multiplying larger numbers, we will get a larger result. So this is some good indicator to start working. Now we know that the multiplication of higher probabilities produce higher number, and thus we can use this as an indicator that our line is better. So let's focus on that a little bit. Well, you see, by using those products, we have a small problem. Here we have just 4 numbers and we don't get easily lost. But imagine what if we had to train on 10,000 points instead of 4 points that we see here? Well, we would have 1,000 products with numbers, all of them being between 0 and 1, and this would be very unstable, okay, and it would produce very, very, very small numbers, and we want to stay away from numbers like 0.00000 something. So now we see that the approach is good, but we need some better solution. What about using sums? Well, you see, sums seem to be a better approach here. So what would be that which can turn products into sums? So it's time for a small quiz, right? What function would turn a product into a sum? Sine, cosine, logarithm, or exponential? Well, the answer is a logarithm. And the reason is the following. You see, the logarithm of a times b is the same as the logarithm of A plus the logarithm of B. So logarithms will allow us to turn products into sums. So this is the way to go. Now, let's play a little bit with that. Okay, so let's apply the logarithm on the probability produced by the sigmoid function for our data. So here we will add the logarithms for each of our cases, and they will produce these numbers. Now, these numbers are negative, as any number that is less than 1 will produce a negative logarithm, right? So we will take the negative of the logarithms, which will give us this number. And many of you might have heard about the negative log loss, and this is exactly that. It's the sum of the negatives of the logarithms of the probabilities produced by the sigmoid activation function for our score based on our linear model, right? And by the summation of this, we get what we call the cross entropy. Now, here we see that the model that is doing bad has a large cross entropy, and the model that is doing better has a smaller cross entropy. Now, a few words about the logarithms so that you understand why they are applied into the cross entropy. Well, as we saw, any number that is closer to 1 is closer to 100% probability, right? And the logarithm of 1 produces the result 0. So logarithm of 1 is 0, so it doesn't add anything to the overall cross entropy, okay? It doesn't contribute to the cross entropy. While the logarithm of 0 is in fact infinity. Now, the closer we are to 0, the larger negative numbers we get. The closer we are to 1, the smaller negative numbers we get. So, by applying a logarithm to probabilities, which are numbers between 0 and 1, we will get the summation of them, which will produce us a number like this. So, the closer all our points are to 1, so the better our prediction, we will get a smaller cross entropy. And the less the probability, so the worse the points compared to our line, the higher the cross entropy. So now the cross entropy is what we're going to use to, let's say, we will use as an indicator to understand how good or bad our line is doing. So now our goal is to minimize the cross entropy. As the smaller the cross entropy, the better our model. And the cross entropy is given by this formula, which we're going to examine right now. So let's look at this formula. Well, you know that we said that we are dealing with a binary cross-entropy problem, and we know that our labels are either 1 for acceptance or 0 for rejection. So we will benefit from that to create a formula that utilizes uh, our y, which is our label, to our benefit for producing our cross-entropy and how this works. Okay, let's take this point for example. And we know that this point is blue because it has a y of 1. Okay, so we know that we have an accepted student in the accepted area, right? So how this works? Let's look at it. We have y equals 1, so we multiply our y by our logarithm of our percentage. And then we add 1 minus ry with the logarithm of 1 minus our percentage. In the case it is red, right? So let's look at this. This will give us logarithm of 0.6 multiplied by 1. Now, since 1 minus 1 produces the number 0, that automatically removes all this part of the equation when it comes to to blue to blue points, right? So this will produce the following result. Logarithm of 0.6 plus 0 times the logarithm of 0.4, which is actually 1 minus our prediction, right? So this, because it's multiplied by 0, will get zeroed. So this is what we get, which gives us the minus of logarithm of 0.6, which is 0.51. So by using, by multiplying by our label, which is always 1 or 0, we use either this part of the formula or this part. Now let's look at this point here. So we have a red point in the red area, right? Now, as we said, we always predict over someone being accepted, how much likely someone to be accepted, right? So for this label that is y0, let's apply this. Now, we know that this person is 30% likely to be accepted, right? Because we got a negative, it's on the negative side, right? And since this guy is on the negative side, we got from our sigmoid a number between 0 to 0.5. So the likelihood for this person to be accepted is just 0.3. But because we have a label 0 here, and that's why he's red, because we were given that this person was rejected, we multiply this 0 by the 0.3, so we remove this part of the formula. But now 1 minus 0 is 1. So now by this parenthesis, we activated this part of the formula, which is 1 minus our prediction. So that gives us this thing, which is 0 plus 1 times the logarithm of 0.7. So this is for the red point, right? So what we have is exactly that. The minus of logarithm of 0.7, which is 0.36. So we've seen how we can, using this formula, we can benefit by our label being 1 or 0 to multiply and and use it on use it for us in order to get better results. Okay. Now let's see about this point. So we have a red point in the blue area. So let's look at this scenario. Well, here we have a red point, which means that it was labeled 0, right? So what happens here? Well, initially, based on our line, we think that this is 90% chance to be blue because it's deep in the blue area based on our existing model line, right? So we use, that's what the sigmoid activation function gave us anyway, okay, for this point. So 0 times 0.9 will be 0. But again, because this is a red point, we have 1 minus 0. So we have 0 this, we have 0 to this thing, and we have activated this one, which is 1 minus 0.9 to give us this 0.1. So we have this outcome, which gives us the minus of logarithm of 0.1, which gives us a high cross entropy of 2.30 for this point alone. Now, let's look finally at a blue point in the red area. Now, here we have a very low confidence. I mean, we know that it is 0.2% likely to be blue because we think it's red actually based on our model, right? So we got a 20% chance of this being red, so of being blue, and that is because we got it is on the negative side, and since this is on the negative side, that automatically means that our sigmoid activation function gave us a probability between 0 to 0.5. Okay, so this is the 0.2 that we see here. That's because exactly our line puts us on the red area. Now, what happens here? Okay, we know that since the point is blue, the label that followed it was 1 while we trained, right? So what happens here is we multiply by this chance, which is a 0.2 likely, and 1 minus 1 gives us 0. So now we have activated by multiplying y here, we have activated again this part of the formula, and we have deactivated this part of the formula, which gives us exactly minus a logarithm of 0.2, which is 1.61. So if we put all these together, we see that we get a high uh, overall cross entropy for all our points here, and here we get a smaller cross entropy for all our points. So this is actually what the cross entropy really does for us, right? But that is when it comes to binary classification problems. I mean, when it is something a yes/no situation. But it turns there are many other cases where we might have a problem that deals with more classes. What happens then? I mean, this is the problem that we have to deal with a multi-class cross-entropy, and it's what we're going to see next. So let's stay with acceptance or rejection scenario. So now, let's say that we have three classes instead of two. Let's say that the first class would be acceptance with scholarship. The second would be just acceptance without scholarship. And the third would be rejection, right? And again, here, since we have more classes, we have more percentages, right? But they need to sum up to 1. Just like in binary classification, where we said that 0.6 likely automatically implies 0.4 not likely, which they sum up to 1. Here with more classes, we just have the same thing. So all our classes should sum up to 1 for all our students. So for student 1, the total percentage per class should sum up to 1, same with student 2 and same with student 3, right? Now, let's say that we are given the labels for our data to train. Now, the label data we got for our three data set points is the following. The first student got accepted with scholarship. The second student got rejected, and so did the third student. All right, so let's see how good or bad we are doing. Well, as you see, these are the probabilities that we need to take into account. And just like in binary classification, where we took into account only the labeled percentage and we discarded the percentage that wasn't on the label for our point, the same thing we do here. So we take into account this, which is our label, and we discard the other two. So what happens? Well, we have now again a set of multiplier of probabilities, which is zero point 0.7, zero point 0.3, and zero point 0.4 equivalently. And if we apply the negative of the logarithms to our probabilities, we get the cross entropy for our multi-class classification problem. And as you see, it's exactly the same thing, just with more classes. Now, this is the formula for the multi-class cross-entropy. And what it says is really this. Okay, let's say for all our classes, where I is our classes from class 1 to class n, okay, and for every point in our data set, which our data set which is j from I to m, okay, so it's like having two nested for loops. So we say for all our data points and for each our data point for all its classes, okay, we will multiply the class um, label by the logarithm of our prediction. And now how we know which one to take into account and which one to discard. This is what the one-hot encoding does, and we will see it in a second. So this is the binary cross-entropy and the multi-class cross-entropy. And when the n is 2, so when we have two classes to deal with, those two are actually the same, okay? Now, let's look, however, how they differ. So here for the binary cross-entropy, we know that our label is a binary label. It can be either 0 or 1. And as we earlier saw, if it is 0, it will silent this part of the formula. And if it is 1, it will silent this part of the formula. Now, equivalently, we said that we silence the parts of the formula that don't belong to our class. But how do we do this here? I mean, here we could get away with a 0-1 situation. How do we do this here? Well, this is where the one-hot encoding comes to play. And as you can see, one-hot encoding is nothing but a matrix. So if we have, let's say, 4 possible classes, we will have a 4 by 4 matrix. If we have 100 classes, we will have 100 by 100 matrix. And if we have 1,000 possible classes, like in ImageNet, we will have 1,000 by 1,000 matrix. Now, for our example here that we see with 4 possible classes, we see that each class is actually a vector of 4 numbers. All right. So the first number activates our class here and deactivates any other possible multiplications. Much likely we had the binary label here that was we could hear this and we silented this one. So we silent every other um, possible multiplications and we keep only per class its own label. So our label now is actually a vector uh, which is from 1 to n depending on the number of classes. So our label for our first class is the vector 1000, and the vector for class 4 is the vector 0001. So these are our labels now. So while we had a scalar label here, it was a number. Here our labels are themselves vectors, and that's what it really is. Now, so by looking at the previous example, we multiply this by 1 and the others are multiplied by 0, so we silence these two and take account only this one because this is what we got as a label, right? So our label is 100 here, and we also had the labels of 001 and 001 for this. So this is how we got the 0.7, 0.3, and 0.4. So this is how the one-hot encoding works in order to deal with multi-class cross-entropy problems. Now, let's see, this is the cross-entropy. So what about our error function? Well, you see, the only problem, the only thing that we need to add here is that the cross-entropy will produce a sum of numbers, but we want to have an overall error. In order to get an overall error, we need to take the average of this. So we simply need to divide by the number of our inputs. So this is what really happens. For our cross-entropy error function, we keep our formulas the way it is, but we simply divide by the number of the data sets points that participated um, in our training. So I'm going back again here. This is our cross-entropy, and our error function is our cross-entropy divided by the number of points that participated, which is just this thing here. So that was it. I hope this video was useful to you. Have a nice day, and thank you very, very much for joining.